All right, so let's get started. We are pre-recording lecture 23 because I'm going to be out of town. So what we're going to do in this example, or in this lecture, is just go through an additional 3D equilibrium problem. I'm recording this a little earlier than we're covering this in class, so I'll try and be a little bit preemptive in what I think I'm going to say about this topic as we get to this in class. But essentially, what we're doing is we're just computing support reactions. We're just computing them in 3 dimensions as opposed to 2. And we've already done one example by the time this video will be public, so this will just be another one. And this one will definitely make the point that whenever you're dealing with 3D equilibrium problems and really 2D equilibrium problems, you generally want to sum moments first before you sum forces. When we did our 2D equilibrium problem, it was sort of apparent just from the free body diagram that summing moments allowed us to eliminate a number of our unknowns, and we'll see the same thing here. Now, just to make sure that we're all on the same page, we are going to be dealing with a system that has 6 equations and 6 unknowns. However, for this problem, when we start looking at our vectors, particularly our moment vectors, we're going to find that one of those unknowns just kind of doesn't show up. One of those equations just kind of doesn't show up. And it's because if we look at the system, we'll see that there are no moments about the z-axis for this system. And it's just because of the way it's configured and the way the forces are aligned and whatnot. That's not always the case. That's just a particular point about this problem. Now, in 3D, there are oodles and oodles of different boundary conditions and whatnot. By and large, the most common ones I would expect you to deal with are either the fixed support or the ball and socket, because the ball and socket are sort of representing it's the 3D equivalent of a pin boundary condition, and the fixed support is just a 3D equivalent for a fixed boundary condition. Maybe cables or maybe ball boundary conditions that only have a force in one direction. But again, 3D equilibrium problems don't really get more difficult dependent upon the boundary conditions that you use. They just get longer. And that's really the theme with 3D problems, is that they're not harder. At least I don't think they're harder, but they do tend to be longer and there's more steps and whatnot. So we're going to spend this video going through this example. I'm going to go ahead right now and just switch right to the notebook so we can get right into this. So we have here a 3D problem. And we have a 48-inch boom. That's this boom AC. So maybe I'll highlight the boom in question just to make sure that we're all kind of seeing the same thing. So there's the boom. Let me get rid of that. Oh, sorry. Let me get rid of that and scroll that back up. So here's the boom, and it's being held by a ball and socket joint at C. And it's being held by 2 cables. We'll call that BF, and we'll call that DAE. Okay. Now that's kind of important for this problem because DAE, it's the same cable from A to D as it is from A to E, so it's going to be the same tensile force. So basically, there's a little loop there at A, and there's a single cable that passes through both of them. So that is incredibly important as we start defining our problem. And then we have this 320-pound weight that's being applied at B, and we're supposed to determine the tension in each cable and the reaction at C. So the first thing I'm going to do is I'm going to just take some time and, wrong pen. Let me go back down here. I copied the free body diagram below so that I could refer to that a little bit later. Actually, let me close OneNote real quick and open it back up because my pen function seems to have frozen. That can happen every now and then. Let's see. All right, so let's go back to here, draw full screen. Let's try that now. There we go, a lot better. Okay, sorry about that. Okay, so the first thing I'm going to do is I'm going to take some time and describe the forces, okay? And I think it should go without saying that our forces are going to be in pounds, but I want to take some time and describe the force vectors that are going to be applied on this problem. And the first thing I want to take some time to describe is my C vector. Okay, and C vector, what I mean by C vector is I mean the reaction at C. Okay, now what I'm going to do for the sake of this problem is, remember, when you're solving for reactions, you need to assume a direction. But we have a reaction in 3D, so what I'm going to do is I'm going to assume a direction, and I'm going to basically assume positive along each of the axes. So we'll call this CX, CY, CZ. And so each of those are going to be independent unknowns that we're going to have to solve for. That's ball and socket reactions are going to have, like pinned, in 2 dimensions, a pin boundary condition has 2 reactions that are independent of one another, and in 3D, a ball and socket has 3. So that vector is going to be CXI plus CYJ plus CZK, and those are unknowns. We don't know what those magnitudes are yet. Now, one vector we are aware of, though, is the weight. We do know what the weight vector is, and if we notice, by weight, I'm referring to that 320 pounds, and that's just going to be 0I minus 320J plus 0K. So we know that force. So that's a force we know, and then the C vector corresponds to a force that we don't know. The remaining vectors are related to the cables. Okay, so I'm going to have one force that goes like this, right? And so these are cables, so they're going to be in tension. So I'm assuming they're yanking on the boom. I mean, if here's the boom, and the boom probably wants to fall down, those cables are sort of propping it back up. So they're wanting to yank on the boom. So there's going to be a force here, a force here, and a force here. Okay, and so we need to name each of those. So let's call that T. Oh, let's write that in black. So let's write that as TAD, TAE, and we'll call it TBF. Now, the way that I'm going to write these, just for now, because they're oblique, they're in 3Ds, so I haven't figured out unit vectors and whatnot, is I'm going to say that these equal, so for TAD, let's just keep our notation pretty simple. Let's say some magnitude times the unit vector, right? I got to figure out what that unit vector is, but for now, we know that's what it's going to be. Now, I would be tempted to say, okay, some magnitude times its unit vector right here, but that's not the case, because keep in mind this AD and this AE, this is all the same cable, okay? So whatever that magnitude is here, it's the same magnitude there. This one is the only one that has a unique magnitude, okay? And again, the reason I'm saying that is because if we look at the boon, so here's the boon, and basically what the problem is saying is that there's a little loop at the end of the boon, and then I have a cable that basically goes like this and then loops like that. So whatever that tension is, that tension has to be the same thing. Hence why those 2 magnitudes are the same, because those 2 magnitudes correspond to those forces. So that's why those 2 magnitudes are identical. Okay? So those are my forces, and ultimately the unknowns that I need to solve for are this, 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 and that. And again, so that it's crystal clear, those have the same magnitude. Those are my unknowns, and that's basically me framing out the problem. Okay, so what I need to do is I need to treat this like any normal, equilibrium problem. I need to sum forces, and I need to sum moments, and I need to set the sum of moments equal to 0, set the sum of forces equal to 0, and solve for my unknowns. It's going to take a little while to get there, but it's not going to be anything appreciably difficult. Okay. So let's get into it, and I copied the free body diagram over again because I didn't want to have to keep scrolling up and down over and over again. So let's start off now by writing some position vectors. Position vectors. These are going to be in inches, okay? So let's figure out what position vectors I'm going to need. Well, the amount of position vectors I'm going to need is going to be a function of where I'm summing moments from. And the principle in 3D equilibrium holds true in 2D equilibrium. You typically want to sum moments where a lot of unknowns are intersecting. So what I'm going to suggest is that we sum moments here. Sum moments here. In other words, at C. And the reason why is because all those C vectors, that C vector, all those unknowns corresponding to the reaction at C all pass through C, so they generate no moment. So the only moments that I need to account for is everything else. So the nice thing about that is I've got 4 other forces to consider. I've got the force here, the force here, the force here, and the force here. But the good news is that I really only need 2 position vectors since since we have pairs of forces that each intersect at given points. So what I'll do is I will define 2 position vectors. I'll define one that goes like this, and so we'll call this R, and we'll say that this is 2A from C, and then we'll define another one that goes like this, and this is R2B from C. Okay. Now you can simplify that however you want. If you just want to write R1 and R2, that's fine. And if you want to use coordinates, that's fine. The nice thing about this problem is that my position vectors, and this is another reason why summing moments at C is such a great idea, is that the position vectors are all going to be aligned along the z-axis, and they're all going to be positive. So writing them out is going to be pretty easy. That R vector to A is just going to be 0i plus 0j plus 48k. And then R to B is going to be 0i plus 0j plus, and then that's 30. Okay, and I forgot a hat right there. So the cross products are hopefully going to be really simple and hopefully be really straightforward. The only other thing that we are going to have to do a little bit of work on is those lambda vectors. Because I can't compute cross products associated with those unknown forces without the lambda vectors. So I got a little bit of work I got to do there. So let me go ahead and copy and paste this one more time. Again, just so I don't have to keep scrolling back and forth, up and down. Hold on, I think it froze up on me again. Sometimes OneNote can be a little tricky like that. My apologies for that. I'm not sure why it does that. Yeah, I'll get to a point where some reason my pens don't want to select. Okay, so now we need to define distance vectors, and this is where a little bit of the work's gonna come into play. So we'll call this section unknown force vectors. And so first we'll start off with distance vectors. These are going to be in inches. So we're going to need 3 of them corresponding to our 3 unknowns. So we're going to need an AD. Okay. So you can do this however you want. If you want to use coordinates, that's fine. If you want to do it by observation, that's fine. But I think you can see that along the x-axis, we're going to go negative. Along the y, we're not going to change at all. And then along the z-axis, we're going negative as well. We're going backwards. Okay, the next thing we're going to need is an AE. We're going to need a vector like that. That one is going to have values in the y-axis, but not along the x. So AE. So this one's going to be 0i plus 20j minus 48k. Again, they're both minus 48 because they both go from A to the wall. So I think that should be pretty straightforward. And then we're going to need BF. So we're going to need that vector. Well, I can do better than that. We're going to need that vector right there. So that's AE. And if you hear my daughter upstairs running, she's just being a toddler. So, okay. So this one's going to be 16i plus 0j and then minus 30k. All right. So that should be pretty straightforward. Move that over a little bit so it's kind of indented. Okay. So there's our distance vectors. Now what we need to do is compute unit vectors. And so we just take the vector and divide it by its own magnitude. I think at this point should be pretty straightforward. So we have that the magnitude of this vector. So one of the things I am doing in this video is I am sort of skipping through a lot of the plug and chug, because hopefully that's something you can do on your own. But that's the beauty of YouTube. You can pause and make sure that you're getting the same values that I am. So for AD, what we're going to do is for all of these vectors, we're going to use the Pythagorean theorem. Let me, again, indent that a little bit so it's sort of under there. So we're going to use the Pythagorean theorem, compute the magnitude. We end up getting the magnitude as 52 inches. That's when it's all said and done. And so therefore, lambda AD is just going to be negative 20 over 52, 0 over 52, and 48 over 52. So that ends up being negative 5/13 plus 0j minus 48, or not 48 over 52, but 12 over 13 times k. So just simplifying that a little bit. And then what we can do is we can go ahead and multiply that by the magnitude. So we can say that therefore TAD is T1 times lambda AD, which is T1 times all of this. All right, so there is one of our force vectors solved out. Makes our life a little easier. So now we just need to do the same thing for the remainders, for the remaining others. So for AE, we just do the same thing, compute its magnitude. We also get 52 inches. So we get a somewhat similar looking vector for AE, although we have to switch some values around. So we get 0i plus, and this one ends up being 5 over 13 j, and then minus 12 over 13k. And so therefore TAE, remember this one's also multiplied by T1. Okay, so make sure that you're cognizant of that. Don't make a mistake and use a T2. So T1 times 0i plus 5 over 13 j minus 12 over 13 k. And so there's our next one. And we just have one more to do. We have BF. All right, maybe what I'll also do is I will take this, I will lower it just a little so it's a little easier to discern. So BF, the magnitude's a little different. It ends up being 34 inches. So therefore, and I'm trying, as I do these calculations, I want to make sure that you can kind of see the distance vector up above. So lambda BF is, let's see, when that's all said and done, you end up getting 16 over 34, which is 8 over 17I, plus 0J, minus, and then 30 over 34 is the same as 15 over 17K. And so there you go. And then we multiply it by its magnitude, which this one is T2. So therefore, TBF is T2 lambda BF, which is T2 8 over 17 I plus 0J minus 15 over 17K. Oh, gotta put that in the parentheses. I'd say the most difficult part about this problem is just the bookkeeping necessary to keep everything in track. That's probably the hardest part. Okay. Now, the next thing that we have to do is we need to compute our moments. Okay, and I'm actually going to, again, cheat and put this image down here so that we have it. Okay, we have 4 moments that we need to compute. And let's actually write those out. Let's write those out. So, moments. Are you kidding me? I'm going to have to close this again. I swear, OneDrive does not like when I copy and paste images. I think that might be what it is when I'm copying and pasting those images. Maybe I'll try and stop doing that. Okay, there we go. Okay, sorry about that. All right, so now what we need to do are computing our moments, or in other words, our R cross Fs. And keep in mind, these are going to be in inch pounds. Now, before we start just doing a bunch of stuff, I actually think it's a good idea to take a step back and make sure that we understand what moments we're computing, why we're computing them, and how we're going to compute them. Because once you figure that out, the rest is pretty mechanical. So remember, we are summing moments at point C, okay? And there are 4 forces that are being applied that aren't going through C. So we don't have to consider the reaction at C. We can sort of ignore that. We have this force right here. We have this force right here. We have that force right there. And then we have the weight. Okay. So what I would argue is that there are 4 moment vectors that we're going to need to compute. And so there's 4 moment vectors that we're going to need to compute. Okay, so we're going to have a position vector crossed with a force vector. Okay, I think the force vectors are pretty easy, right? So this is going to be TAD, TAE, TBF, and this is going to be our weight vector. But just making sure that you're using the correct position vectors. So for both of the first 2 moments, for the AD and the AE, both of those are going to use that longer position vector, that RAC that we computed a little while ago. So what we're going to do is we're going to use RAC AC here, R, AC here. And then for the remaining two are going to use that shorter position vector, R, BC. So R, BC, R, BC. And those are our four forces generating moment at C. I mean, keep in mind there is still, that reaction that goes through C, but if a force goes through a point in question, it does not generate any moment. So we do have to consider it when we sum forces, but not when we sum moments, because it's not generating any moment. I mean, we could have, if we want, we could say, maybe what I'll do is I'll say note. We could have MC is R, maybe CC crossed with, the C vector, but that's going to be 0 crossed with C, which is 0, right? So there's nothing to handle there. All right, so I'm an engineer. I like tables, so let's see if we can organize this in a tabular fashion. So we'll say component. We'll put R. We'll put that in inches. Then we'll have a force vector in pounds. Then we'll have R cross F in inch pounds. And let's see what we get. So again, we're going to have AD, AE, BF, and then W. Okay. Now, for the first one, or for the R vectors, we're just going to have 0I plus 0J plus 48K. Same thing here. But then this is where it changes. And that's 30K. 0I plus 0J plus 30K. Okay, for the F vectors, so let's go back and let's make sure we're being diligent here. So maybe what I'll need to do, let me erase this because I don't want to squunch this. I want to do this well. So let's see. So for the first one, we have T1 times -5/13 I plus 0J minus 12/13K. And then this one is also T1. This is, let's see, 0I plus 5/13J minus 12/13K. There's probably a more efficient way of doing this in your homework calculations and whatnot. Again, the bookkeeping is incredibly important. So 8/17 plus 0J minus 15/17K. I did sort of leave everything in fractional format. That way, if you're doing the calculations on your own, you can check your answers and whatnot. And then this one is 0I minus 320J plus 0K. All right, so there's our force vectors. Actually, let me see if I can squunch that up a little bit. So let's do that. Do that. Do that. That's a little neater. Okay. Now I am going to move this over and make sure that this is clear how this goes. R cross F in inch pounds. Now, if you're computing this cross product, remember you've got this these magnitudes that are out the side, so don't forget that. So let me just sort of set one up off to the side, And so if we wanted to compute MAD, what would we be doing is we would be saying I, J, K, 0, 0, 48. So you can see I'm taking off that first row. And then I want to have negative 5/13, 0, and then minus 12/13. But then don't forget, by that whole thing, I'm multiplying T1. So basically, I'm just taking that T1 and factoring it out, and I'm crossing all of that. And so when it's all said and done, and so I would handle each of these one at a time. So first off, do the cross product. So for the cross product, we have I, and we have 0, 0, 48 minus 12 over 13. Let me erase that. 13 minus J, and then we get 0, 48 minus 5 over 13 minus 12 over 13 plus K, and then there's 0, 0, 0 minus 5 over 13. Then that whole thing is multiplied by T1. Don't forget the T1. So maybe what I'll do is I'll really indicate that. I'll use squiggly brackets. Okay. And so when it's all said and done, what ends up happening is, this one goes to 0 because you have 0 minus 0. This one goes to 0 because you have 0 minus 0. The only thing that you have is negative J times, and then you have 0 minus 48 negative 5/13. So you got to track your negatives because there's a lot of negatives in there. So what do we have? We have a negative times a negative times a negative. So negative, and then this ends up being negative 48 times 5 is 240. So it ends up being 240 over 13 T1. Negative 240 over 13 T1 times J. Okay. So what I've done is I've collected all of the constants multiplied by J, or all the constants multiplied by I, or all the constants multiplied by K. So this is just showing you how one of the answers comes out. So let me take this and sort of move it down, and we'll sort of just put this in a little thought bubble. So what I'm going to do here in this first row is I'm just going to write negative 240 over 13 T1 times J. Okay. So when I start writing the rest of the answers, I want you to understand where they came from so that you don't see, well, how they just show up on the page. Let me go ahead and write the rest of those out so that you kind of see what happens. So for MAE, you end up getting negative 240 over 13 T1 times I. That's what happens when you do all that multiplication. For BF, you end up getting positive 240 over 17. And this was going to be in T2 times J. This is J. Let me do a little bit better job. I think my I's and J's might get a little mixed up. All right, so that's J. That's I. Or tell you what, yeah, we'll just leave it like that. And that's J. Let's just make sure that's clear there. And then for MW, there's no variables for MW. It's just numbers. So this ends up being 9600 I. So that's what happens when you sum everything up. And so I've done one for you. I'm not going to repeat and do all the others. But I think you can see that if you carry that out, you should get, a pretty straightforward response. Okay. So where are we at in the problem? Okay, so let's scroll up and down, and let's make sure, get rid of that. Let's scroll down, let's make sure that we're clear on what we've done from start to finish. So here's the problem. So the first thing that we did is we wrote out all of our forces, okay? And we had to do some work to describe those unknowns, but ultimately we've described the unknowns, then we described the position vectors, We fleshed out that description for the unknowns by, force times unit vector, or magnitude times unit vector, and then we took care of our cross products. So now what? So now we can start applying the equations of equilibrium. So now we can start actually getting into solving the problem. That's one of the things you'll find in the land of statics, is that sometimes it takes a little while to actually get to the point where you can actually start doing some work. So let's look at static equilibrium. Like I said in the very beginning of the problem, it is usually always advantageous to sum moments first. So let's handle sum of moments equals 0. Okay, so let's see what happens. Okay, now what I'm going to do is I'm going to write each of my moment vectors. But I think by now you've seen me do this, where what I'll do is I'll write them, but I'll sort of organize them very well, and I'll say MW. I'll organize them in such a way such that, okay, MAE was the one that had the I component, and so did MW. And then MAD had the J component, so it was negative 240 over 13 T1J. And this one also had positive 240 over 17, sorry, 17, not 117, 17 T2 times J. So this is just me organizing them in a little bit of a, go away. This is just me organizing them in a little bit of a columnar format, because ultimately what I'm doing is I'm summing those coefficient terms, right? So if we look at summing up everything, let's say in this blue box, this is summing up moments about the x-axis, and that has to be equal to 0, okay? Same thing over here, this box over here, this is summing up moments about the y-axis equals 0. So this is where, even in 3 dimensions, you can be a little strategic in what order that you do things, okay? So let's take a look at this. If I sum moments in the y first, I'm going to have an equation with a T1 and a T2. So there's 2 unknowns in that rightmost column. But what about summing moments in the x direction? If I sum moments in the x direction, I get 9600 plus a polyjunct times T1 equals 0. So I can solve for T1 directly. Let's do that first. Let's sum moments, let's move that down a little bit. Let's sum moments about the x-axis. Let's see what we get. So we get negative 240 over 13 T1 plus 9600 equals 0. So therefore, T1 equals negative 9600. Just move the 9600 over, flip and multiply, negative 13 over 240, and there's the answer. And so when you chug that out, you get T1 is 520 pounds. Remember, all our forces are in pounds. That's one of our answers right there. Pretty simple, okay? Now what we can do, now let's sum forces in the y direction. Or sorry, sum moments, sorry. I should say sum moments. Now let's sum moments in the y direction. So we get negative 240 over 13 T1 plus 240 over 17 T2 is 0. Okay? So now we know what T1 is. Negative 240 over 13 times 520 plus 240 over 17 T2 is 0. And I think by now you should see this is pretty straightforward to solve. All I need to do is bring the T2 over. So let's see. So 240 over 17 T2 is 240 over 13 times 520. And then multiply both sides by 17 over 240. And so T2 just equals that. So we see that the 240s cancel. And so we get 520 over 13 times 17. And when it's all said and done, we get 680 pounds. The solution part on this problem should be very, very, very easy. And I think there's something to be said about the fact about how this problem is formatted, because the way that the unknowns were aligned, the fact that there were that there's one cable that's serving as the unknown for two forces, those are some things that make this problem a little bit easier to solve. This problem's been structured in such a way that the math shouldn't be too terribly challenging. Okay, I don't need to do that. All right, so there's summing moments, okay, and summing moments yielded the unknowns in the two cables. Now, if this was an exam problem and the only thing that you were asked for was the tension in the two cables, you're done. But in this problem, if we go back to the very beginning, let me go take my mouse pointer over here. If we go back to the very beginning, not only were we asked for the tension in each cable, but we were also asked for the reaction at C. Okay, remember, we've got those unknowns at C we have to handle. And fortunately, that's really easy because now the only thing we have left to do is to just sum the forces. Okay, and what we'll find is that that's, in order to solve for the unknowns, it's very, very simple. Okay, so now what we're going to do is we're going to sum forces equals 0. All right. Now here's what I'm going to do. All right. Let me drag this down a little bit. I don't want to get in the way of what I'm doing. Okay. So let's write down the vectors that I know off the top of my head. So I know C is CXI. Let's put a little bit of space there. CYJ plus CZK. We can do that. Now we have our W vector. We know that. So 0I minus 320J plus 0K. But we have three force vectors. Okay. Now watch this. Now, what was TAD? Let's recall. How do we get these tension vectors? Well, it equals, the better part with that equals. We take the tension times the unit vector. Well, now we know what those tensions are. We know that the tension in rope 1 is 520 pounds. We just solved for that. So now what I'm going to do is I'm going to take that unit vector and multiply those terms by 520. And so what happens when you do that is you get negative 200I plus 0J minus 480K. And again, if you're wondering how I'm doing that, I'll put a little asterisk over here. We'll put this down here. So how do we do that? So TAD is T1 times lambda AD. T1 we already figured out was 520 pounds, right? And then lambda AD is negative 5 over 13I plus 0J minus 12. Oh, I need to scroll that up. Sorry about that. Over 13K. So all I'm doing is I'm just multiplying that out. So that's going to be, so we'll say negative 520 times 5 over 13 times I plus 0J plus negative 520 times 12 over 13 times K. And when you chug that out, you get negative 200I plus 0J minus 480K. So now that we know those tensile forces, we can distribute all that out. So let's go ahead and do that. So when you do that for the remaining two, you end up getting, let's see, 0i. You end up getting positive 200j. And then minus 480k. And then for t BF, you end up getting 320i plus 0j minus 600k. That's what happens when you chug all that out. And again, now the math is really, really easy because, again, what we're doing is we're looking at these columns of coefficients and summing them up. I'm weaving in and out of here because all I care about is the coefficients, the constant coefficients. So this is sum of the forces in the x direction equals 0. Maybe what I'll do is I'll capture the signs here. Let's make sure I'm capturing the signs because I didn't use parentheses when I handled that. So this is the sum of the forces in the y direction equals 0, and then this is the sum of the forces in the z direction equals 0. Again, a little messier than I probably would have liked, but you know, you can kind of see how that works. And so should be pretty straightforward. So if I sum forces in the x direction here, let me put a little thought bubble around that just to show you that that was sort of a calculation we did off to the side. So if we sum forces in the x direction, we get cx minus 200 plus 320 is 0. So therefore cx is minus 120. If I can probably squinch that other one in. Sum of the forces in the y direction equals 0. cy minus 320 plus 200. I think cy is going to be positive 120 there. And then if I sum forces in the z direction, so cz, what do we get? Minus 480 minus 480 minus 600 is 0. So 480 and 480 is 960. 600 is 1560. So CZ is 1560 positive. And so that's pretty much it. So therefore, our C vector, this is our reaction vector, is negative 120i plus 120j plus 1560k. And again, that's in pounds. And then don't forget that we had T1, which was 520 pounds, and then T2, which is 680. And that's it. That's the answer to the problem. Okay, so hopefully you found that this was pretty straightforward. I know it's long, which is one of the reasons why this 4.3 homework assignment is extended over a couple of days, just to give you time to chug through it. But I think you'll find that this is pretty straightforward. So with that, that's all I have for this video. I think what I'll probably do is we'll have our in-class lecture on Wednesday. I'll post this probably on Wednesday, and then that homework assignment you'll have until Monday to get done, so you'll have a fair amount of time to complete it and a couple examples to follow off of. That's all I have, everybody. I will see you all on when we get back. You all have a wonderful weekend. We'll see you then.